like other physical properties, uh, resistivity is also no exception. It also vary with temperature. For here, this graph shows the resistivity of a copper as a function of temperature. The dot on the curve here marks a convenient reference point at temperature T naught is equal to almost 293 Kelvin, and resistivity is around 1.69 10⁻⁸. The relation between temperature and resistivity for copper and for metals in general is fairly linear over a rather broad temperature range. For such linear relations, we can write an empirical approximation that is good enough for most engineering purposes, that is rho minus rho naught into T minus T naught. So T naught is a selected reference temperature, and rho naught is the resistivity at that temperature. And usually we take T naught 293 K, which is room temperature. And rho naught is for copper, it is 1.69 into 10 raised to minus ohm meter. So yes, and because here in this temperature is we take only a difference, is taken as a difference in this equation. So it's not a big deal to use either a Kelvin. It doesn't matter much either you use Celsius scale or you use Kelvin scale in that equation, because the sizes of the degrees of these scales are identical. And the quantity alpha here is called the temperature coefficient of resistivity, and is chosen so that equation gives good agreement with experiment for temperatures in the chosen range. This one. So let's look into Ohm's law. Okay, let's discuss Ohm's law. And we know a resistor is a conductor with a specified resistance. It has the same resistance no matter what the magnitude and direction of the applied potential difference. So some other conducting devices might have resistances that change with the potential difference. So how we will distinguish such devices? So a potential difference is applied across a device which we wanted to test, and then the resulting current through the device is measured at as V is varied in both magnitude and polarity. So the polarity of V is arbitrarily taken to be positive when the left terminal of the device is at a higher potential than the right terminal. The direction of the resulting current would be from left to right, and it's arbitrarily assigned a plus sign. The reverse polarity of potential with the right terminal at higher potential and this one becomes the negative. The current causes is assigned a minus sign. So this here a plot of I versus A versus V is for such type of device. This plot is a straight line passing through the origin. So the ratio I over V, which is the slope of the straight line, would be the same for all values of V. So this means that the resistance R is equal to V over I of the device is independent of the magnitude and polarity of the applied potential difference. Now let's look into this plot here. This is a plot for an other conducting device. Here current can exist in the device only when the polarity of V is positive and the applied potential difference is more than 1.5 volts. So when current does exist, the relation between I and V is not linear. Here it was linear. It depends on the value of the potential difference V. So now we are able to distinguish two types of devices by saying that one obeys Ohm's law, this one, and other does not. So Ohm's law is an assertion that the current through a device is always directly proportional to the potential difference applied to the device. So assertion is correct in some situations, but still for historical reason we use the word term law for Ohm's law. For this device or this one, it turns out that for 1,000 ohm resistor, the trend shows that this resistor is obeying Ohm law. The device here shows that this is not obeying this device not obey Ohm's law, and this is a case of a PN junction diode. So a conducting device obeys Ohm's law when the resistance of the device is independent of the magnitude and polarity of the applied potential difference. So V is equal to IR is a contended statement of Ohm's law. Sometimes it's not true, like here in this case. So we can generate we can generalize this form of Ohm's law for conducting materials, like we can say we know we can generalize it in this form: E is equal to rho J. A conducting material obeys Ohm's law when the resistivity of the material is independent of the magnitude and direction of the applied force. So now instead of dealing with potential and current, we are dealing with the current density and electric field. So all homogeneous materials, whether they are conductor like copper semiconductors or like pure silicons or silicon containing some impurities, obeys Ohm's law within some range of values of the electric field. If the field is too strong, however, then they are departures from Ohm's law. So then they don't obey Ohm's law. So let's have a look into microscopic view of Ohm's law. In our first lecture, we already discussed drift velocity. So now let's discuss it again to understand or to get more understanding of the Ohm's law at microscopic scale.